Your mission, shall you choose to accept, will be to build an uncrewed aerial vehicle with mission Maverick at Embry-Riddle Aeronautical University, Daytona Beach. Are you ready?
We analyze the completion requirements according to the SUAS completion rulebook. A game chart has been prepared in September, and we have gone through all the teams, and we divided into sub-teams like build, software, business, and flight, and we have achieved everything according to our expectations. This is our mini Mugen aircraft, which is planned with the autonomous flight plan, which is required for the SUAS completion. We have included an autonomous flight controller in it, and we have given a remote ID to that. The flight requirements of this Mugen is exactly matching with the SUAS competition. Its flight time is around 2 hours. The minimum requirement is 30 minutes, and the maximum speed of our mini Mugen aircraft is 67 miles per hour.
For a brief system overview of the system and design elements that we chose, we went with a fixed wing platform called the Mini Mugen. It's a consumer drone you can purchase anywhere. It has a carbon fiber fuselage which houses all system components. We selected a Pixop Cube Orange to act as the flight controller, and there are redundant systems to act on top of the Pixop's GPS, specifically a Holy Bro GPS unit. Our radio transmitter and receiver are both FrSky. The power comes from a 10,000 milliamp battery. Our telemetry from the laptop ground control station to the airframe is a telemetry module, and the controller utilized by the safety pilot is an FrSky Tyrannus QX7 2.4 GHz radio transmitter.
The aircraft has 2 cameras, one for drop zone identification and another for obstacle avoidance. The camera used to identify the drop zone is an SIYI-A8 Mini. This camera is capable of 4K resolution and is mounted on a 3-axis stabilizer with optical zoom capabilities. This is mounted on the bottom of the fuselage with the lens pointed at the ground. After a waypoint has been completed, the system will transition to a drop zone scanning state in search of the specified position. This works by traversing the drop zone in a lawnmower pattern. As our aircraft makes its way around the drop zone, our imaging system named AeroViz will first search for the color of the target to avoid unnecessary image processing. Once the correct color has been identified, a yellow V8 model is used to identify the shape of the object. If the color and the shape are a match, then the vision system moves on to the third stage, detecting the character. This works by isolating the character and using Tesseract, which is an OCR package to identify the character. For object detection and avoidance, an Intel RealSense depth camera is used to spot any potential targets. By using another YOLO model, if the system predicts that a foreign aircraft trajectory intersects with ours, the system will transition to a receive state, manually updating the roll and pitch of the aircraft to avoid the threat. The image classification systems were first tested using synthetic data to confirm the model's work before field testing. By printing out sample standard objects outlined in the competition rulebook and using a mannequin, our team conducted field tests to confirm and improve on the vision system. Additionally, we tested the time it took from the first appearance of the object in frame to when it was properly classified.
The airdrop design mechanism was uniquely designed in order to meet all the mission requirements. It was designed using Inventor software, and a team, including myself, started coming up with this design around November 2023 and has manufactured it using PETG 3D printing. So the design for the drop mechanism was printed with PETG filament. As you can see here, it will attach to the underneath of the Mugen and controlled with a servo, which is attached to an Arduino Nano, which will be controlled with the Pixop and dropped once the detection system detects the drop point. At that point, this pin here will pull from the signal from the servo, dropping the package, which is a very simple design. It's just 2 clasps around the bottle held by the pin and will be dropped down with the parachute. Alright, for testing the parachute selection, we did it by dropping off the 3rd floor of our engineering building. And this was to find a properly sized parachute to make sure that it descended at an acceptable rate.
Our communications are managed through the PX4 flight stack interfacing with the Q ground control software. We use radios operating in the 2.4 and 5.8 GHz bands. Data transmit includes real-time critical flight data, system statuses, video streams, and control signals that allow for manual override. Our system is designed to achieve a predicted communication range of up to 2 kilometers with a throughput sufficient of up to 720p video streaming and telemetry data without latency or disruption. The system was tested by flying the aircraft during the mission testing days and analyzing the quality of the data received. We maintained an average throughput of around 12 megabytes per second, more than enough to stream video and send telemetry data with 100% uptime during flight testing. Testing the communication loss set our aircraft to a return to home state, performing a landing in case of a loss of communication during competition.
The RFD 900X telemetry system is a high-performance radio modem for long-range communication between the ground control systems and UAV. When we talk about the long range, the RFD 900X offers extended communication range compared to standard telemetry systems, making it ideal for applications where a UAV need to operate over large distance. Its range up to 10 kilometers, and it's a compatibility for every popular autopilot system such as Pixoc, Autopilot, and other, making it is easily to integrate into existing UAV setups. We are using a mission planner software, which is a powerful ground control station software used for planning, executing, and monitoring missions or UAVs and drones. Mission planning, real-time monitoring, configuration, calibration, and payload control. These all the extra features which can be seen in the mission planner. For our flight, we are going to plan a machine, giving waypoints to our flight and getting a position, certain position where we need to drop the payload. These all are given in the mission planner.
Our aircraft we decided to go with is the Mini Mugen. It's a completely carbon fiber aircraft with a wingspan of 2.6 meters and a total length of 2.05 meters. The Mini Mugen was originally designed to be a gas-powered aircraft, but instead we modified it to be completely electric, and it runs on one 10,000 milliamp hour battery for a duration of 2 hours. Mini Mugen's empty weight is 6.5 kilograms with a max takeoff weight of 15 kilograms, and it can carry a payload of 4 kilograms. At full throttle, the Mini Mugen can reach a maximum speed of 67 miles per hour and a cruising speed of 54 miles per hour. We decided to select a Dual Sky 380 kV motor with a 20x15 propeller attached. The center of gravity of the Mini Mugen is placed 97 millimeters from the edge of the wing, connecting to the fuselage. We have marked the optimal weight and balance location on the edges of the wings to measure before each flight.
We utilize a YOLO model for real-time object detection, which scans the video feed from our A8 Mini to identify potential obstacles. Once an object is detected, the algorithm predicts its trajectory and assesses whether it poses a collision threat based on its projected path relative to our aircraft. If a threat is determined, the system transitions to a reactive mode, where the primary goal is to avoid collision. This involves dynamically adjusting our aircraft's pitch and roll through the PX4 flight stack API to maneuver safely away from the obstacle. Once the object is no longer deemed a threat, the system transitions back to its original flight path, continuing on its mission. Before real flight testing, the system was tested within the simulated gazebo environment. This allows us to tweak the algorithm without risking a real crash while providing data for continuous optimization. In our preliminary test, the system successfully identified and avoided obstacles in 85% of our scenarios, with an average reaction time of 0.5 seconds from threat detection to maneuver initiation. After ensuring these systems operate reliably in the simulated environment, we then conducted limited field tests. This testing framework aims to ensure that once deployed, our aircraft can confidently navigate through the competition airspace, adhering closely to the flight path and mission objectives.
When planning out the design constraints and the mission objectives, we had a lot of options in terms of the airframe, which is really the central decision when you're beginning to take on a task like this. We originally started off with a multi-rotor design that had 4 upward-facing quadcopter motors and 2 forward-facing nacelles. This allowed us to have a VTOL type setup that we originally hoped would be very efficient in terms of transitioning from ground takeoff to flight. Our original line of thinking was that if our airframe was capable of vertical takeoff and landing, it would be more maneuverable and be able to deliver packages with speed and accuracy. However, this didn't really pan out. Our VTOL was very slow, and for the competition, the maneuverability was not something that ended up being advantageous enough to make it worth. It was also a very small airframe and would have been subject to a lot of movement from wind, turbulence, etc. And due to this small form factor, having a heavy enough battery to power the airframe would have caused it to be even slower, and there would have been a lot of diminishing returns on that decision. We also had, as an emergency backup, a slew of quadcopters that were really just checking all the boxes in terms of mission objectives.
Mission Maverick has rigorous safety protocols put into place pre-flight, active flight, and post-flight. When we're in our lab working on the UAV, we utilize safety glasses, gloves, and hearing protection when applicable. We ensure our team members all have their long hair tied back and loose clothing, and we ensure that everyone wears closed-toed shoes and long pants while working on the UAV, both in the lab and out in the field. In the event there is a fire present in the lab or during our on-ground operations, we will contact 911 immediately and contact our advisor. In the event there is a fire present on the ground during our ground crew operations or in the lab, we will use a fire extinguisher to try to control the fire. If not, we will immediately contact 911 and contact our advisor for further assistance. In the event a battery were to spill, we will reference our battery spill kit and take necessary action to use baking soda to neutralize the battery acid. We will also reference the Embry-Riddle Environmental Safety Risk Assessment sheet and contact our advisor. We will report all chemical spills to the Embry-Riddle Environmental Health and Safety Report Spillage Form.